when we are going to talk about specific heats for ideal gases. We need to specify that if it is at constant pressure or at constant volume. And for the constant volume process, where the volume is going to stay the same, Q, the heat, should be N, the number of moles, times CV times delta T. At a constant pressure, we are going to have QP equals NCP delta T. Now, both of CV and CP can be calculated for a monoatomic ideal gas. Monoatomic means, remember, this one is the one with one atom only. And these are the members of group 8, like helium, argon, neon, okay? And we can actually calculate these using the following equations. CV, the specific heat at constant volume, it is 3/2, and the specific heat at constant pressure, it is 5/2. The difference between the two values is 1 R. Okay, then this is these are equations that you need to know. Now, although this calculation was done for an ideal monatomic gas, it works well for real gases at low pressures. We'll say when we have very few, we said a thin gas. Okay, helium, it is 0.99 R. Okay, for nitrogen, it is 1 R. This is the difference between CP and CV, okay, which ideally should be R. For nitrogen, it is 1. For oxygen, it is 1. For argon, it is 1.01. And for carbon dioxide, 1.01. And for methane, it is 1.01 R. Then it's it is, it works well also for real gases. Now, the second law of thermodynamics, it is a statement that we're going to see that we are going to have it more than one statement for the second law. But it is mostly, I will say, about, processes that can occur and the ones that they cannot. There are many ways to state the law, and we are going to maybe go through more than one. The first one here, this is the first statement. Heat can flow spontaneously from a hot object to a cold object. It will not flow spontaneously from a cold object to a hot object. And this is really here, spontaneously means naturally, without having any machine. Then if you have your cup of coffee, you're going to find that the heat is going to be transferred from that hot or warm to the cold. Okay, and of course the reverse will not happen. Okay, it will not go from the room to the cup unless there is a certain agent that is going to do that work. We will talk about this. Now, the development of a general statement for the second law of thermodynamics was based in part on the study of what is called heat engines. And what are really heat engines? These are devices that converts heat into work that we can use it. Okay, and we have one of the most popular, let's say, examples is the steam engine. Okay, then where we are going to have a fuel that is gonna heat the water, and then the vapor, it creates a vapor or steam, and then expands and do work against the piston. And here, and that is really the vapor condensing back again into water again, and the cycle repeats, so that this process is gonna be a continuous process. Now, in all heat engines, we have a high temperature reservoir, which is really the one that is making the things warm. And we have a cold temperature reservoir where the heat is going to be expelled. And we have also, I would say, a cyclic engine that is going to make work to be done. Now, to allow heat to flow from TH to TC, and some of that heat flow is changed into work. Okay, then we will see that QH here is going to be equal to W plus Q cold. Now we will discuss only engines that run in a repeating cycle. The change in internal energy is going to be zero because it is a complete cycle, closed cycle. The high temperature reservoir transfers an amount of heat, QH, to the engine, where part of it is transferred into work and the rest is Q cold. Now I will say this is gonna be expelled to the cold or to the lower temperature reservoir. Note that all three quantities are really positives. Now, in a steam engine, steam forces motion and then cools and condenses. It could then be heated and then the process would repeat. And this is what we said here. We want to have something that it is gonna go in repeating cycles. Now, I will say here is really we are explaining the process. An internal combustion engine is another good example of a heat engine where we are going to have here an intake where I'm gonna take the gas, and then I will compress it, and then we're gonna have a system that is gonna create a spark where it's gonna ignite, and then is gonna make the expansion. We call this power stroke, and then we are going to get like some of this is going to be an exhaust valve where that is going to be expelled. Why does a heat engine need a temperature difference? This is because the work done on the system is one part of the cycle will equal to the work done by the system in another part, and the net work will be zero. Now, this is how we're going to calculate the work. It is Q hot minus Q cold. And this is, of course, also related to conservation of energy. One of the parameters that I'm looking at, it is the efficiency of a heat engine, which is how efficient it is in creating that work done, work divided by Q hot. And since W, it is Q hot minus Q cold, I can have my efficiency as 1 minus Q cold over Q hot. In order for the engine to run, there must be a temperature difference, otherwise heat will not be transferred. Then if you have both of them at the same temperature, hot minus cold is going to be zero, and then the efficiency is going to be zero. Now, there is an ideal engine. We call it the Carnot engine, and that was created to examine the efficiency of a heat engine. And I will say it does not have an friction. And then I will say each here process in the cycle, it is reversible. Now, the Carnot cycle consists of first isothermal expansion, which means here increase in volume at constant temperature, and then here adiabatic expansion, which means here this is gonna be without any Q leaving or entering the system. And of course, it's going to be also a volume increase. Number 3, isothermal compression, because remember, we need to go back to, and that is, again, it is decrease in volume, but at constant temperature. And then adiabatic compression, again, this is where we are going to have Q equals 0. And just here, a reminder that when we talk about isotherm, this is the one, and adiabatic is going to be steeper, then don't forget. An example is on the next slide, which is this one here. Okay, number 1, isothermal expansion. Okay, then amount of heat is gonna be enter, which is gonna make the system is gonna be expanding, and it is represented by the isotherm from A to B, and then is gonna be from B to C is gonna be adiabatic expansion. There is an increase in the volume, and of course the temperature is going to be changing from the hot to the cold or to the low. Now after that we are going to have the third process is going to be isothermal compression. Then it is at the same temperature you are going to have a decrease in the volume, and then you are going to have an adiabatic compression, and this is like closes the cycle. The maximum efficiency heat engine is described in Carnot's theorem. If an engine operating two constant temperature reservoirs, it is to have maximum efficiency. It must be an engine in which all processes are really reversible. In addition, all reversible engines operating between the same two temperatures, they have the same efficiency. Then it depends on the initial, the high temperature and the low temperature. And versus now we can have the E as maximum as T hot minus T cold over D hot, which is 1 minus T cold over T hot. Then for an ideal reversible engine, the efficiency can be written in terms of the temperature. From this, we see that 100% efficiency can be achieved only if the cold reservoir is at absolute zero, which is impossible. And because of that, the real engines that we have, they have some frictional forces, and they have really a kind of 60 to 80% of the Carnot value of efficiency. Then it's an idealization that doesn't exist in actual life. The maximum work that an engine can do, it is W max equals the maximum efficiency times Q hot, and it can be written as 1 minus TC over TH times QH. If the two reservoirs are at the same temperature, the efficiency is zero. The smaller the ratio of the cold temperature to the hot is going to be, the closer the efficiency. Here we have an example. A Carnot engine performs work at the rate of 440 kilowatts while using 600 calories of heat per second. If the temperature of the heat source it is 570 degrees Celsius, at what temperature is the waste heat exhausted? Now, of course, we're going to assume a perfect Carnot engine where the efficiency can be calculated as TH minus TC over TH. We are given a power and a heat, so that we need to use both efficiency equations, which are this one and this one here. E equals W over H hot, and I will divide by T both on numerator and denominator to get the power. And then after that, I'm gonna make them equal to each other here. Here, it doesn't hurt to divide both terms by the same value. And then I have derived an equation here for T cold, which is gonna be that term here. And then it was calculated as 713, and that is 440 degrees Celsius. Don't forget that you have here the temperature in Celsius, and that should be converted into Kelvins. Now, another system of we will talk about is refrigerators or air conditioning systems and heat pumps. These appliances can be heat engines operating in reverse. okay? Like why in reverse? Because they are cooling. By doing work, heat is extracted from a cold reservoir and exhausted to the hot reservoir. And then here Q hot is going to be equal to Q cold plus W. Okay, this is here the heat engine and this is the refrigerator. Then I am doing work, and that work plus QC is going to be Q hot. More heat is exhausted to the kitchen than it is removed from the refrigerator. An ideal refrigerator would remove the most heat from the interior while requiring the smallest amount of work. This ratio is called the coefficient of performance, COP, and it has to do with QC divided by the work. Typical refrigerators have a coefficient of performance values between 2 and 6. Bigger is much better. Okay, here we are really representing an air conditioning system, and it is very similar to the refrigerator. And here we have the cold reservoir is the interior of the house or other space which we intend to cool, and the hot reservoir is the outside environment, and we are exhausting and air conditioning within the house will result in the house becoming warmer, just as keeping the refrigerator door open will result in the kitchen becoming warmer. You can recognize this. If finally also, like, it's the same for the heat pump. Now the heat pump is the same as the air conditioning, except with the reservoirs reversed. Heat is removed from the cold reservoir outside and exhausted into the house, keeping it warm. Note that the pump does actually contribute to the desired result, a warmer house in this case. Okay, now this is the equation that we are going to use for an ideal heat pump with two operating temperatures. Okay, W equals Q hot minus Q cold. And finally, also, we are going to get the coefficient of performance, which is a Q hot divided by W. I want you to compare this one with the one for refrigerator, Q cold divided by W. This one, Q hot divided by W. The last quantity maybe we want to talk about is entropy. It is a reverse, when I have a reversible engine, we have the following relationship that was derived. Q hot over Q cold divided by Q hot equals TC divided by TH. We can actually rewrite this equation by just rearranging things. And then we're going to have Q cold over T cold equals Q hot divided by T hot. This quantity, which is the same for both reservoirs, is defined as the change in entropy. Then Q over T, we call it change in entropy. We use for entropy S. Okay. Now, a restaurant refrigerator has a coefficient of performance of 5. If the temperature in the kitchen outside the refrigerator is 29, what is the lowest temperature that could be obtained inside the refrigerator if it were ideal? Then here I have coefficient of performance for a refrigerator. It's Q cold divided by W, and then Q cold by W. Q cold. W can be calculated as Q hot by Q cold. And if we go to ideal, it's going to be in terms of temperatures. And then I can rearrange and have my TC, okay? And remember again to convert your 29 degrees Celsius into Kelvins. Then I will say the lowest temperature is going to be negative 21 degrees Celsius. This is the definition of the entropy, the change in entropy, Q over T, and it has units of joules per Kelvin. For this definition to be valid, it's like we should have the heat transfer reversible. In a reversible heat engine, it can be shown that the entropy does not change. Now, a real engine will operate at a lower efficiency than a reversible engine, and this means that less heat is converted into work, and therefore we are going to have that delta S total is going to be minus Q hot over H hot plus Q C over TC. Any irreversible process results in an increase in entropy. This is important. And any irreversible process results in an increase of entropy. Now, to make it general, the total entropy of the universe increases whenever an irreversible process occurs. The total entropy of the universe is unchanged whenever a reversible process occurs. Since all real processes are really irreversible, the entropy of the universe continually increases. If the entropy decreases in a system due to work being done on it, a greater increase in entropy occurs outside the system. As the total entropy of the universe increases, its ability to do work decreases, and the excess heat exhausted during the irreversible cannot be recovered, and doing that would require a decrease in entropy, which is not possible. Now, there is a connection between entropy and disorder, and when we talk about this, we can think that as entropy as if it is an increase in the disorder of the universe. In this diagram, we have the end state is less ordered than the initial state, and the separation between the low and high temperature areas has been lost. Then this is here where we have low temperature, and here we have high temperature. Now, if we look at the ultimate fate of the universe in light of the continual increase in entropy, we might envision a future in which the entire universe would have to come to the same temperature. At this point, it would no longer be possible to do any work, and nor would any type of life will be possible. This is referred as the heat death of the universe. All right, let's do this here. 1100 kilogram cars are traveling 95 kilometers per hour in opposite directions when they collide and are brought to rest. Estimate the change in entropy of the universe as a result of this collision. Okay, this is T equals 293. Okay, now assume the loss in the kinetic energy was a transfer to the environmental heat flow. Then we will say that delta S equals 2, because we have two cars, times 1/2 mv0 squared divided by the temperature, and this is going to be the change in the entropy of the universe. What is the change in entropy of 1 cubic meter of water at 0 when it is frozen to ice at 0? Now, that one here, we will use the heat removed from the system to make it like to make the change in entropy of when it is gonna be converted into ice. Then I will say delta S is gonna be Q over T. It's not to melt the ice, it is to form here the ice. And this is the reason why it will be expelled. The heat is taken away. then Q over T, and that is going to be minus M times the latent heat of fusion and divided by temperature. We know that the mass is going to be rho times V, then I can calculate the mass. I know the LF, like it's given here as a constant, and the temperature, it is 273 because it is 0 plus 273. There is a third law of thermodynamics talking about absolute zero is a temperature that an object can get arbitrarily close to but never attain, which means we cannot attain the absolute zero. Temperatures as low as 210 to minus 8 Kelvin have been achieved in the labs, but absolute zero will remain ever elusive. There is simply nowhere to put that last little bit of energy. And this is called the third law of thermodynamics. It is impossible to lower the temperature of an object below to absolute zero in a finite number of steps. Here is the summary of the chapter, and that is your chapter 18. Thank you, and see you soon. Bye.